In this video, we're going to look at derivatives of circular functions or trig functions. And these are the formulas that appear on the methods formula sheet. And they are actually chain rule versions of the derivatives of sine, cos, and tan. So if you just had sine of x and you were trying to find the derivative of sine of x, the derivative of sine of x is cos of x. If you're trying to find the derivative of cos of x, the derivative is negative sine of x. And if you're trying to find the derivative of tan of x, then it's 1 on cos squared of x, which is a circular function that we call sec squared of x. Now sec is just like the other trig functions or circular functions. You can find it on the unit circle. So we'll just go in here so that we know the x coordinate of the point here is cos of x, the y coordinate of that point is sine of x. If we go out to the tangent line, we get this distance as being tan of x, and this distance from the center of the circle to where that radius line extended touches the tan line is sec of theta or x, and it's the secant length. This is the tangent length and this is called secant of x. Now you don't need to know that. That is not in the methods course at all. So all you need to do if you are asked to find tan of something is to write it as 1 over cos squared of whatever it is, or use the sec squared version. So let's have a look at how sine of the derivative of a sine graph is in fact a cos graph. So I'm going to use this little interactivity from Geogebra, and you can see that at this point here there's a blue line, and that is the tangent line, and the gradient of this tangent line is 0. And so this little point here on the graph is showing you that currently for this particular x value, the value of that gradient of the tangent, which is in fact the derivative, is 0. And then we're going to move it along and we're going to watch what happens to the slope of the line and the size of the slope of the line and the graph that it creates. So here we go. Pick up the line and move it along. You can see that the tangent now has a negative gradient. So if we go the other way, it was sloping positively. So now it has a negative slope, and you can see that it's getting steeper. And so the value becomes steeper. That had a slope of -1. Now it's getting less negative, and you can see the less negative value being plotted. At that point there, it's 0. Now we have a positive gradient, which is as steep as possible up to 1 at 0. There's another gradient of 0, so we have an x-intercept on our graph. And you can see that what we've generated there is in fact the cos curve. And so for all our points on the graph where our derivative was equal to 0, here, here, and here, you can see that the gradient function actually has an x-intercept for those particular values. And so our derivative of sine of x is in fact cos of x. So let's have a look at the same thing with sine of x and watch the derivative graph being graphed. So we're just about to come up to a point. At that point there, horizontal tangent, so the gradient is 0, and hence the blue dot is appearing at 0 on the y-axis. Maximum steepness of 1 there, up to 0, and you can again see the shape that we're generating here. And what you can see is that we are getting, if I just fill in the dots, we are getting an upside down and inverted sine curve. So if I drew the sine graph on here, it would go up and come down. And so what we've got is a reflection of a sine graph. And so for our cos graph, what we've got is that the derivative of cos is a reflected sine curve. And now for the fun one. So again, I'm going to let the derivative function get generated, plotting itself on this graph, and it's only going to do it for a tiny little section. So you can see that the gradient at that point is very steep. It's getting less steep, so less positive. It comes down, but it's not zero. It's still got a positive gradient at that point, and then it starts to get steeper again. And so it generates this U-shaped graph. If I bring it back down and try and fill in the dots for you, you can imagine that derivative graph heading up towards infinity up this way. And as I come back down, it's still here, it's getting bigger and bigger and bigger. And so what you end up with is a graph that is U-shaped in between this one and this one. And if I did the same thing on the next version of the curve, you would get the same thing here and here and here. And this is our graph of sec squared. So these are just some more patterns that you need to remember, some more derivative patterns. And as I said at the start, the formula on the formula sheet are attempts at chain rule. And so let's chain rule these. You can see I've got outer functions in green and inner functions in yellow for all of these. And so if we wanted to find the derivative of sine, the derivative of sine is in fact the cos graph, and so our derivative is cos of x squared, and we need to multiply that by the derivative of our inner. So this will be 2 cos of x squared. If we did the derivative of this second one over here, so we know that the derivative of our cos curve is a negative sine curve, so it's going to be negative. We're going to have the derivative of this inner function, which will just be f dashed of x, and it's sine of whatever function we started with. So we're just using our derivative patterns, that the derivative of sine is cos, that the derivative of cos is negative sine, and for our tan one, all we need to do, now it doesn't matter which one you use, you can either use the sec squared version, and in that case it would be the derivative of the inner section, which will be 6x plus 2, and then we just write sec squared and the original function, 3x squared plus 2x. Or if we wanted to do it as our 1 on cos squared graph, it will be the derivative of the inner function over cos squared and then the original function itself. Either of these is fine. You don't need to know, as I said, you don't need to know what sec squared is. The most you need to know is that sec squared is 1 on cos squared. That's all. So the very last thing I wanted to leave you with is a much more complicated version of the chain rule, and that's simply because you're asked to find the derivative of a function that is a cubic function, a cubic of a trig function that is that is a function of a particular angle. So if you like, we've got an outer function, an inner function, and an even inner function. And so what we do with our chain rule, same as before, we make our outer function y be a function of u, our inner function, and within our inner function we've also got a t. And so we can rewrite our original equation as y is equal to u cubed, because our u is going to be cos. And our u is cos of the little blue bit inside that we've labelled as t, and t is 2 theta squared plus 1. So what we then do is exactly the same as what we've done with the chain rule before. We find dy du, which is 3, let's just go through here, which is 3u squared. Next we find du with respect to t, and so the derivative of cos is negative sine of t. And finally we do dt d theta, and so theta is the thing we're differentiating with respect to, and so the 2 is going to come out and multiply the 2, so we're going to end up with 4 theta. And now we're going to put the whole chain rule together with all of those things linked together. And what's going to happen, you can see that dy d theta is equal to dy du times du dt times dt d theta. In effect, the du's cancel and the dt's cancel, and we're left with dy over du. So let's put those formulas in and see how that works. Let's just move this up a little bit and substitute in our formulas. So dy du is 3u squared minus sine of t and 4 theta. We're going to need to replace the u with cos of t, and we're going to replace the t's with 2 theta squared plus 1. So let's go ahead and do that. So you can see I've replaced the u with a cos and the t with the 2 theta. Replace again and we get this giant thing here. And now that, if we tidy that up just a tiny little bit, that will give us our answer in a useful form. So the coefficients 3 times -1 times 4 all to combine to give us minus 12 theta. We've got, and then we're just taking our cos squared thing here, and I'm taking the squared from the end and I'm writing it in the shortcut spot, and we can leave it like that. Now, a lot of people will look at this and think that they can factorize that out. Please do not try and factorize that out. It's not a common factor. Do not factor out, do not try and factor out the 2 theta squared plus 1. Sine and cos have no meaning unless they are tied to an angle. So although we refer to them as sine and cos, you can't have sine and cos written in mathematics in a formula like that without an angle associated with them.